to welcome you for this webinar. My name is Rocio Garcia Alonso. I work at Sustainable Innovations, and I'm also the Communications Manager for the TEMPEST project. It's actually the first to speak at this webinar. And I would also like to introduce my colleague, Daniel Matilla. He will be supporting the questions and answers at the end of this webinar. I think you can also see him on the footer. And
Hi,
just
good
give
morning.
me, hi, hi, Danny. And
Well,
we are more,
welcome.
we're
Yeah, go ahead, go
also
ahead.
45 participants, so maybe one more minute. And as I was saying, this webinar is being recorded. So if you need to leave in half an hour or something, this video will be available on all of the project's YouTube channel, and also the presentation. You can download it in PDF, I think, at the end of next week. So thank you for being here. And I think, yeah, we're right on time. So I think I will start presenting all these 7 new and not so new EU-funded battery research initiatives. As I was saying, we will start with Jeremy Warren. He's the project coordinator of TEMPEST. Then we'll be followed by Alvaro Sanchez. He actually is the project coordinator for 2 projects. The first one is Fastest, and the second one is Extended. And then we will go with Lisa Lu Gracia. She's the project manager for VERSAPRINT. And after her presentation, we'll go with Yosu Sendoya. He is also coordinator of the BATS project. And then with Sara Daneshi, she's coordinated the NEXTCELL project. And then we will finish with Miko Palatier, and he's coordinator the NEXTBAT. And after this, the speakers will have for like 5-7 minutes to present their project, and then we'll have 15 minutes for the questions and answers. I think the chat is available, and thank you so much for being here. And we're right on time, so I will give the floor to Jeremy, and thank you. If you have any questions, just write on the chat. Here we go.
Yes, hello, my name is Jeremy Warren. I'm the coordinator of the TEMPEST project. I'm also the chair of the EU Ingenious cluster, which regroups 5 of the projects that were funded under the same call. Next slide. The TEMPEST project regroups many partners across a wide group of countries, and we are focused entirely on the goal of reducing both the size and weight through, amongst other things, using composite systems. And since the composite systems have different behavior as opposed to metal systems, we are looking at implementing technologies which will render them safer and more reliable for use in the long term in several different applications. We are focusing on medium mobility applications, large-scale mobility applications, and stationary storage. And we will work to scale those technologies and then translate to direct market application. And this is a collaborative effort which is financed both by the European Union and the United Kingdom. Next slide, please. So the technologies we want to put in place is, first of all, to reduce the amount of weight and increase the power density. So we will implement a cell-to-pack architecture to increase both the gravimetric and volumetric density of power. We will develop new battery management systems, which will connect some of our other technologies, which I'll get to in a moment. TEMPEST will apply both to typical lithium-ion and solid-state battery systems. So we will try to make a very flexible toolkit for the future generation of batteries. We'll implement novel thermal control systems both to preheat cells at low temperatures and to maintain optimal operational temperature for cell types that need to be maintained at a higher operational temperature. In order to ensure the safety, amongst other things, the composites, we'll integrate a structural health monitoring system to actively detect any fissures or defects as they are created, and that will communicate to the battery management system to alert any users as soon as they are detected. In addition, the battery systems will include both flame retardant and resistant systems to deal with any flame issues. There will also be coatings inside the batteries to extinguish fires as if they occur. And we will implement thermal management systems to better evacuate the heat. And in addition, the outside of the battery housing will be coated with a impact resistant coating to better resist the impacts of, for example, rocks and other debris. In addition to assure sustainability, we will implement sustainable reversible joining methods that will allow us to better disassemble the batteries at the end of life. We will also implement hydrogen-based recycling methods to extract, recover, and basically reuse out of black mass all of the metals that go into the electrodes and the components of the battery. And then we will implement digital tools to improve the performance and efficiency of the batteries, which will be part of the battery management system. Next slide, please. So we are focusing on achieving 70% improvement in battery recyclability, a 30% improvement in cost of manufacturing, 15% improvement in battery performance, and reduce weight by 15%. Next slide. Is that it? Next slide. Okay. This will lead to a reduction of greenhouse emissions by 62%, reduce energy loss, and increase range by up to about 50%. And based on the overall usage of batteries to which we focus on applying this, you can see up to a reduction of around 78 tons of CO2 removed per battery pack per year. And this will reduce the overall energy load up to about 72% on battery charging systems, which are connected to stationary storage systems. Next slide, please. And so the partners of this are AP Plus Rescol, for which I work, then Fraunhofer ICT, ABEE, University of Patras, the National Institutes of Chemistry, KTU, Techniker, Sustainable Innovations, the University of Bath, the Institute of Advanced Automotive Propulsion Systems, and Albion Technologies. Next slide, please. I think that's it.
Yeah.
Thank you very much,
Thank
Jeremy.
you.
So next speaker will be Álvaro Sánchez, who is the project coordinator of both Fastest and NEXTCELL project, and he's also part of the AB team. So I will give the floor to him, and any question that you may have, please ask in the chat or in the questions and answers. We will answer all of them by the end of the presentation. Thank you very much. Álvaro, the floor is yours.
Thank you a lot, Daniel. It's a pleasure for me to be here. I will be introducing all of you to the Fastest project. So first of all, which means fastest. Yes. Fastest stands for Faster Hybrid Testing Platform for the development of battery system. Later on, we will go more deep, but the project is a duration of 3 years and 4.7 million euros funding for the European Commission and as well for UK. On the right side, you can have a map with all the partners involved: AVI, University of Ljubljana, FEV, Fraunhofer, BNZ, VTT, AVI, Robuster, Flanders Make, Ikerlam, Mondragon, Energy, and Sustainable Innovation. Next slide, please. What is the objective of the Fastest project? And the Fastest project focus on the development of the validation and rapidly deployable test platform for the use case design of the experiments for the DOE to obtain robust results. This platform integrates both physical and virtual testing of multiple scales which will facilitate faster and more efficient research and development on the battery system, ensuring the safe, fair, reliable, and durable in the design. In terms of prototyping, the project takes a holistic and interconnected approach through the hybrid rapid test platform from the perspective of a global test facility. Advances the service such as DOE algorithm, virtual tested, digital twin. Inside FastTest, we have 3 different use cases that are electric vehicles, stationary application, and off-road. And the platform will be tested for the 3 use cases. In the project, we are using 3V generation batteries and solid-state batteries as well. Next slide. So some objectives of the project are to develop the fast trust hybrid platform, to lay down the pathway for the result exploration and dissemination, to develop and validate the physics basis on the data-driven models, and set up the digital twin information management architecture, and to stockade the proposed efficient DOE strategy. Sorry. Beyond the results, the main task of the project is the creation of the platform, which of course requires the development of many parallel structures, such as physics basis model, data-driven model, and so on. Each of these sub-tasks has a different tier L, technology readiness level. From the tier L4, from some tasks, for example, for the DOE, and higher for some of them as the digital twin to the tier L6. Next slide. Here's some KPI of the project. I have already mentioned we have 3 different use cases, and we will try to reduce the operating time in 20%. We will reduce as well. Increase the safety, reliability, and performance virtualization ratio, and the communication between all the communication should be less than 15 milliseconds in the computational time. Next slide, please. So for the implementation, we start with the design of the experiment with the DOE at the beginning, and then we pass to the specification and use case definition. I mentioned 3 of them. And in parallel, we are developing some models, physics basis model and data-driven model for performance and aging, and at cell level and module level, in different cells, in 3V generation and solid state. So we have a lot of development of modeling here. Then, in parallel, we have the battery safety and reliability, EA-powered toolchain, and we put everything inside the digital twin for the hybrid test in the battery development. And then at the end, we develop this whole hybrid platform. Next slide. So I think that here is a more clear overview. For you is from the left side, we have the links at the DOE where we put everything together. We are designing which type of tests we want to perform at the beginning, and we communicate all these things to the digital twin. On the top left, model development, the work packet 3 and the work packet 4 is all the models that we are developing inside the project, and we will put all these things inside the digital twin. The digital twin is like a management for the model, a data collector, user interface, and so on. But we will not run in the model, let's say, inside the digital twin. We will run the model inside a platform that, which the name is XMod, and we will run all the model over there, and we will communicate all together, not just for the virtual test, as well for the physical test bench. So we will connect everything through the data platform. In real time, as much as real time that we can, for sure. And I think that's all. Next slide.
That will be all for fastest.
Yeah, just in the last slide we have. Okay. Yeah, okay. So Now, for
As we
extended,
mentioned in the beginning of the webinar, Alvaro is also a coordinator of the extended project.
yeah, both of them. So we move now to the extended project. I don't think I need to introduce myself again. So what extended means, it's next generation of multifunctional, modular, and scalable solid-state battery system. Next slide, or yeah. Well, it was not mentioned at the beginning, but it's almost 5 million euros funded just for the European Commission. 3 years as well, same that fastest. What is the main ambition of Extended? Our goal here is to design, develop, and validate the next generation of battery systems that meet the growing mass market demanding the electric vehicles and for another application as well. We are focused on the developing efficient, lightweight, eco-design, and multi-purpose battery system with significantly reduced charging times. Our design will enable passenger vehicles to achieve a range of more than 500 kilometers normal driving condition, that to optimize energy storage capacity, a lifetime of at least 300,000 kilometers, and monitoring by advanced battery management system designed for both the first and the second life. Here, I want to mention before go that we are using both cells for the solid state in the fastest as well. I forgot to say that. I just to mention because I know that we are using solid state in another project, but with another different shape. So just to clarify that. Next slide, please. And so, yeah, some of the objective that we have in the project is the development of the modular battery system, and reduce the complexity of the battery management system by reducing the wires. We are trying to use wireless for the communication between the sensor and the BMS, increase the energy density, the thermal safety, and simplified manufacture for the recyclability and the second life. Develop and validate the modular and scalable thermal management solution for the solid state for high cells performing and low cell degradation. As you know, there is no so much information on the internet or some paper where you can find information about the solid state. And we will try to test and qualify of the battery system performance for various applications. Carbon footprint reduction and design optimization for the solid state system for second life application and for recycling, and define decarbonization strategies for the future transport mobile application. Next slide, please. So in terms of methodology, we start with some baseline identification. I think we can go directly to the right picture. We start with the baseline identification of battery requirement. Then in parallel, after we have a conceptual design, we work together in parallel for the electrical solution. As I mentioned, we are trying to use wireless wireless communication, and then thermal solution is focused on the solid state. There is no so much information, as you know, so we are testing cells in-house. Mechanical solution for the casing, for the cells holder, and so on. Then all will be inside or involved for the safety and security. So we are performing some safety tests in-house as well for the project, and with all this information, we are able to develop some modules for the project. I didn't mention, but we have 3 different use cases as well: electric vehicles, stationary, and aviation inside the project. And then for each of them, we have to manufacture three modules. So at the end, we have 9 modules that we have to prototype and testing by the end of the project, just to check that everything what we try to develop is working properly. And then, let's say at the end or in parallel as well, the sustainability exploitation assessment, we are trying to design the packs for, how to say, for a good second, like a good dismantling. So in order to do that, we have to think before design the system. We have to think how it could be disassembly in order to define how we want to assemble the models of the pack. Next slide, please. And then we have the implementation is the timeline for the project. Let's say we start. We are right now in the green box in the middle. Let's say with Webpack 6 with a safety modular and scalability safety together. With working with the electrical solution, the thermal solution, and the mechanical solution in parallel, and the testing and validation or the developing of the final design will be produced by the end of the next year. So if you follow the social media, you will be informed about that. Next slide. Yeah, some key results for the project, some simulation framework for the solid-state batteries. As I mentioned, solid battery modules defined for the electrical, thermal, and mechanical. Solid-state battery packs and solid-state development and assembly service. BMS hardware and software for solid-state. Battery system design and sizing for the different use cases. Trading of various battery system, and BMS wireless connection. Next slide. Yeah, some target groups, so who could be interested in the project or in the results of the project. Some manufacturer, some safety provider, engineering service, mobility industry, academic community, policymaker, yeah. Maybe all of the persons that is involved in this webinar.
Thank you very much, Alvaro. Very interesting contribution. We have many questions now, so we encourage the people to make more. Next speaker will be Lisa Lu Gracia. She's part of CEA team, and she's the project manager of the VERSAPRINT project. So Lisa, the floor is yours. Welcome to the webinar.
Thank you so much, Daniel. So hi, everybody. My name is Lisa Lu, and I'm the project manager from CEA for this project, so VERSAPRINT. So you can go to the next slide. So as you can easily see from the title, so this project is about versatile printed solution for a safe and high performance battery system. And the next slide, to introduce you quickly to this project. So in a nutshell, CEA is the coordinator of this project, and it's a project that is that will go for 3 years, and it is now about 1 year old. And all these partners are that you can see here are involved in this project, so both industrial and research centers. Now, next slide, please. So building on what we already know about the problems linked with the emissions from the transport sector and leading to the general electrification context, we have to design new and better battery systems, and all these challenges that you can see here, so the manufacturability, the performance, safety, lifespan, or where we or the challenges we have to target, while fostering for circular economy and cost effectiveness. And S is missing here. And so next slide. So it's precisely where VERSAPRINT is coming into play, where we are trying to target those challenges at system level. So we are working around the cell. So it's around the cell level, mini module level, and module level. And the particularity of this project is that we are using additive manufacturing processes that allows us fast prototyping, and that gives us access to wide versatility. And next slide. please. So going deeper in our technical innovations that we are working on, that we call also building blocks. They are mainly led by research centers. And you can see, so the 3 different levels I have set. So at around the cell at cell level, we are designing, we are printing microchannels directly at the cell surface to to have a very efficient thermal management, a very efficient cooling management. And so this should impact the safety, so delay the thermal runaway, and also increase the lifespan of the battery in the end. We also print sensors directly at the cell surface, so to measure the temperature and hydrogen. And now at mini module level, we are mainly working on bus bars. So we are designing completely new bus bars. On one side, we are working on multifunctional ones. So for example, to use them as fuse or to help us to dissipate the heat. And we are working on another side, we are working on easy to dismantle and non-welded bus bars. So this should allow us to make the process of the assembling and dismantling much faster and easier, and removing some steps in the middle. And finally, at module level, we are mainly focusing on the safety, so to increase the safety while reducing the weight of the module. So we are mainly talking about the casing here, where we replace we are using new materials. So for example, self-reinforced polymer, SRP, that allow us to have a very strong stiff material and very light also. And making the process of the recycling much easier and more efficient, as it's only one polymer used for the whole casing. But to this, we will add more eco-friendly additives, such as phase change material and flame retardant, to again improve the resistance for against the thermal runaway, and to delay and to avoid the propagation of the thermal runaway. We are also designing a completely new exhaust gas management system here. And now next slide. To apply those technologies, so to industrial applications, you can see here that we are working with a very wide set of applications, automotive, aeronautics, waterborne, and actually many others, to striving for versatility, of course. So for this, we are developing a decision tool based on a simulation tool that will help and that will guide the end user to find the best combination of those building blocks and innovations for their own application. And all along this project, the manufacturability, the recyclability, the cost, and the environmental impact will be assessed. And now going to the next slide, please. Thank you. To validate those innovations at TRL 5, we are going to build two physical prototypes, thanks to our industrial partners, and one for the automotive and one for the aeronautics. And of course, for all of the other applications, including those two, we are going to validate them using simulation at system level. And going to the next slide, finally, all this collaborative work will be put and is put at the service of impact that will help us to improve the safety, to improve the performance, the lifespan, and reduce, while reducing the environmental impact of those new battery systems, and also trying to help and guide the end user in the decision making. And I will finish this very short presentation, so it doesn't really allow us to show results. So we hope that we can show you some results in a next event. but you will see afterwards in another slide all our contact info and social media where you can see and contact us and see our results. And we will also be present, just to add, at the Battery Innovation Days in Barcelona, so don't hesitate to see us there. And I will finish with thanking you for your attention, and thank you to our partners also.
Thank you, Lisalu. So next speaker will be Yosu Zendaya. He's from CEDETEC, and he's a BATS project coordinator. I would like to remind the participants that if you have any question, this will be very helpful if you express to which project is addressed this question in the chat. This will be very helpful for the Q&A session. So Yosu, I don't have anything else to say, so the floor is yours. Welcome.
Okay, thank you very much. First of all, thank you for arranging this webinar and inviting us to this webinar. And yes, next slide, please. My name is Josu Zendoya. I work in CEDETEC, which is a research institution in San Sebastian in Spain. And yes, and this topic, this BATS name stands for Safe, Efficient Battery System based on Advanced Cell Technology. The cell technology we are using, it is Gen 3B, okay, and we are working with cylindrical cells. As you see in the duration of the activity, we just started in January, and the project will last for 3 years. As you see on the right, we have partners from several countries. We have from Austria, AIT and MIBA Battery Systems, from Germany, Accurec, VUV from Belgium, IFPEN from France, FPT from the Iveco Group from Switzerland, and then from Spain we are UNE, C Automotive, Lomartov, and CEDETEC. The funding is about 5 million euros from the European Union, and there is also an additional funding from the Swiss government. And the main goal of the project is to design and manufacture a battery system based on the cell-to-pack concept, and with a special emphasis on covering the safety events, and especially fire and thermal propagation. And the aim is to be, let's say, useful for several types of transport and mobile applications, and the integration in the vehicle, in this case, is not included in the project. Next, please. So we are not starting from scratch. We start from a concept of one of our partners, which is the macro cell concept of MIBA battery system, and the aim finally is to reach TRL 5. We will simulate the whole system, but regarding physical devices, we will finally demonstrate the concept with 5 to 10 kilowatt hours prototypes of up to 400 volts. And the main key innovations that we are proposing or developing in this project are, from the thermal point of view, we will use a flex cooler device, which is a specific development of one of our partners that is sticking very well to the cylindrical cells in order to improve cost, efficiency, arrangement time, weight, and safety. And we will also optimize the thermal management system through 1D and 3D modeling of these events that I talk about, and also the usual operation of the battery. From the mechanical point of view, we will take care of selecting the minimum amount of elements, and also elements that are environmental friendly, taking also a look to the cost, weight, and of these elements. And we will include, as I said, elements that are useful in order to avoid thermal propagation and fire barriers. I must say that the flex cooler itself has already some properties in order to avoid this thermal propagation, but it could be necessary adding additional ones. We will see, depending on the simulations that we will execute. And from the electrical point of view, we will customize the bus bars to optimize the space, to make them multidisciplinary. We will work also on a DC-DC converter, and a bidirectional DC-DC converter. We will introduce the silicon carbide technology in the power switch device. and we will work on we will work with ultrasound sensors and ultrasound wireless technology. All of this attached to a predictive thermal management system, and we will be aligned with the ongoing activity on the battery passport concept, and we will also take care of the end-of-life activity by proposing a self-made software. Please, next, please. So these are the 3 use cases that we have in the project. We will have we are having a construction vehicle and a leisure boat as first life, and for the second life, a stationary application which is called Volt Station. So we will also take care of this shift between the first and second life, diagnostic, how to do it, disassembly, all the matters that are related to this shift. And we will analyze the system, as I said, from the mechanical thermal point of view at 3D level, and then we will produce some samples of 400 volts in order to test it and as a proof of concept of the overall design that we are proposing. And this is all. As my colleague said, we also will be in the Batteries Innovation Day in Barcelona. So then, or whenever you want, you can access us by checking the email that you will see afterwards, or by checking the website. And that's it. Thank you, Daniel.
Thank you, Yosu. So next presenter will be Sara Zaneshi. She's from VEV France, and she's also the NEXTCELL's project coordinator, which is a special one for me because I'm the communication manager for this project. So Sara, welcome to the webinar, and the floor is yours.
Good afternoon, everyone. Thank you, Daniel, for presentation. Yes, NEXTCELL is another European project of the Horizon Cluster 5, led by FEV, co-coordinated with IB and SIE. In NEXTCELL, we are 17 partners from top industry, research centers, and university. As you can see from the map, we are around like 8 countries, 8 European countries. I need to mention that we have partners, Solvay, which will be spin-off to Cisco with affiliation. The amendment is in the process. For the NEXTCELL, as the name is clear, we are together united for toward next generation of high-performance lithium-ion battery cells. The project duration is 48 months. We turn to the second year, January 2024, and we have almost 30 months of hard work and innovation ahead. The project budget was about 80 million euros funding from European Union. Next slide, please. So as you're aware, like lithium-ion battery market is entering to a period where energy density improvement and cost reduction are leveling off for current generation. And but however, we have like still room for to reach like fundamental limits in upcoming generation. That's why in NEXTCELL we aim to provide a new lithium-ion cell generation for both high capacity and high voltage application by developing and validating groundbreaking jellified cell concepts, for which we need several innovation in the cell material level. Means electrodes, jellification of the electrodes, anode, cathode. Also separators in combination with a high voltage stable gel electrolyte, which could aim to the complete jellified cell concept. Next slide, please. In the consortium for the objective of NEXTCELL, for the operational objectives, we aimed for high energy density, safer safety, cheaper, and sustainability. We are aiming for excellent performance in high capacity and high voltage applications. We are looking for intrinsically safe cells to avoid the presence of low boiling point components. Also, reduction of around 50% in energy consumption, and aiming on the optimization and optimization of manufacturing process for reducing capital and operational cost of the gigafactories. Next slide, please. The impact of project as we are aiming, as indicated, 50% of energy consumption reduction, is more than 70% on recycling efficiency, and 90% of lithium recovery. How we have planified to get through in the project, we have split the project through 9 work packages. Actually, for the work plan, we revolve around 3 dimensions: prototyping, the jellified cell concept, modeling and simulation of the jellified cell concept, and evaluation of technical safety, sustainable, and cost improvement. As you can see, the prototyping is the core dimension of the project. We're feeding and sourcing data from 2 other dimensions, means modeling and simulation, and technical validation. In the prototyping dimension, actually, we aim to start from the material development of jellified cell components, which would be in work package 3, and then to assembly of small scale cells up to 500 milliampere, which would be in the work package 4, and the large scale cells with capacity of 20 ampere hour and 5 ampere hour, which would be in the work package 6 as a final prototype for the concept validation. The TRL will be TRL 6. That's it. Thank you.
Thank you, Sarah. So we are going for the last presentation for this webinar. In this case, we have Miko Pilati, who is the project coordinator of NEXTBAT, and he is part of the VDD team. So, Miko, the floor is yours. Thank you very much and welcome.
Thank you, Daniel, and good afternoon, everyone. It's very nice and a pleasure to join this webinar on next future of battery technologies, and I'm glad to present our project NEXTBAT, where VCT is the coordinator, and several other partners, of course, contribute in central roles. So we are part of the call for next generation battery systems, technologies for battery systems for transport electrification. And we want to put forward several innovations and prototyping tracks to look forward to future solutions meeting end user demands. Let's go forward in the presentation. So generic data here, we started last year, so approaching 1 year, totally 3.5 months, for 3.5 years, 42 months of duration. And as said, we are coordinating, and let's a couple of slides ahead, let's look at a few additional partners, of course, who we have on board here. So next slide, please. Summarizing, some of the key targets for this call, of course, to look into sustainability carbon footprint by also looking into new technologies for relevant for battery systems, that's including battery cells, next gen cells, but also how they are packed into systems, fulfilling and meeting various requirements by the end users. And maybe one of the angles of NEXTBAT, we also want to bring the emerging use cases and add understanding on how to design battery systems for those. Some keys there, energy density, power density, and as we know, these are often also a bit conflicting. If we want more efficient thermal management, for example, then it tends to counteract then the energy density and so on. So some of the design bases might be partially conflicting. So that's why we need to, besides physical prototyping, also do virtual prototyping on that. Battery system weight, lightweight materials, joining techniques for those. Lifetime management, aiming at improved lifetime, also innovative management and sensing so that we are better aware of the state of health of the systems. Next slide, please. So the ambition here is to provide the safest, interoperable, sustainable battery system with the said improvements in performance, energy density, power density, safety all along the lifetime. Manufacturability, also the end of life, looking holistically into the LCA life cycle assessment. Having a standardization and safety in a comprehensive approach, and also in the end, the cost element will be essential for many battery systems and including the applications. So lifetime management and monitoring of that as we go in the application will be very important. So a combination of several factors that play. Next slide, please. So to reach this, we have listed several objectives. The first four on here. So first of all, standardized safety assessment methodology. So and that plays, of course, at cell level, but very importantly also at the module or system level, where we need to have both technology that is safe, but also then at system module level to know how fire propagation, for example, deals with. Framework of requirements. And as said, we have many multiple use cases and they are different combinations of requirements, design basis. Then third, we design prototypes, innovative prototypes, configuration architectures, and analyze how each of the use cases match with that. Digital twin, the software virtual design and digital twin goes along the line as we will progress. Let's look into the next one, where we have the rest of the objectives. Thank you. Hardware elements. So then there will be innovations putting forward the hardware, for example, cell level sensing. Immersion cooling is one of the things, innovative prototyping tracks. 2 prototypes will be manufactured and tested, validated, all the way to the safety validation as well. And looking forward from the prototyping towards further deployment or industrialization. So then a roadmap towards the certification of the next gen. And then, of course, we want to look forward to the market, emerging market, and what it means in a wider context for the battery systems. Thanks. Next one, please. I will not spend too long time here, but maybe just looking at the logos here. So we have, besides VDT, we have RISE from Sweden, 2 institutes of Fraunhofer, IBI and ILT. Then from Switzerland, CSEM, doing one of the prototypes together with CEA. From France, Aplus from Spain, INEO from Spain, and Zabala, BSC, Barcelona Supercomputing Center, Valmet Automotive, Sunlight, and Hart Aerospace, representing also the end-use segments. So it's kind of requirements. Pillar 1, digitalization, modeling, virtual design. Pillar 2. Pillar 3 will be much around the demonstrators, prototyping, validation of the approaches and the innovations we make. Pillar 4, creating the wider impact and looking forward to emerging business. Next one, please. As said, many use cases, and each of these, it's a mixture combination of different factors that play in with different weights. For example, safety, lifetime, refurbishment cost of vehicle installed battery, how it's made. We're not going to be directly the cell to chassis type of approaches. It's more like the back design and isolating the innovations there. I would maybe like to mention long haul trucks, heavy duty vehicles, off-road side, non-road mobile machinery, and then also the airborne segment that we will look into in this respect. Next slide, please. There will be 2 prototypes on generation 4B or 4A. One seems to be a semi-solid state cell, but we will do that, maximizing the energy density and designs for that, liquid cooling, and then the prototype 2, both 48 volts, will go for maximum power density with immersion cooling, and also we will have a cell level management with large format cells. So there will be like quite close monitoring of cells at cell level. And of course, we will do then cross like virtual design, additional prototyping tracks with a view to more developing tailored or approaches or concepts for different other applications. Let's go forward to the next slide. And I already mentioned much of that. Innovations, liquid cooling, immersion through immersion cooling, battery safety assessment methodology, innovations that we will go through towards the prototyping and validation tracks. Virtual design, quite comprehensive physics-based model, digital tools, conceptual design, architectural design tools. Then the system designs, including materials, lightweight materials, next-gen cells, thermal management, then the packing solutions, and finally the manufacturing, for example, laser welding and joining different material combinations. And so looking as the expected outcome, the outlook to next generation of battery systems. And I think I'm almost finished here. So next one, please.
This was the last one, actually.
Okay, great. So then I'll just put it back to you, to the moderator. Thanks.
Thank you so much,
Thank you
Mikko,
very
for your
much.
presentation and for the rest of the speakers. Before we proceed with the questions and answers with my colleague Daniel, I would love to show you the contacts for every project. And maybe Danny can give again the technical guidelines for the Q&A, and I will just pass the slides. Again, this PowerPoint, we will share it. So if you want the social media for every project or the website, this is going to be available. Thank you so much.
So let's start with the Q&A session. As I mentioned before, you can both ask questions for any project or for all the projects through the Q&A in the option in the Zoom, or you can ask as well in the chat. But please say to which project is the question addressed or if it is addressed to all the projects just mentioned it. I would like to remember as well that we are not going to answer specific questions regarding work opportunities or business opportunities. This is a technical webinar, so we are only focusing on the projects and the scope of the projects, methodology, and these kind of questions. Okay, so we do have many questions for most of the projects, so I will start with the first project. So Jeremy, if you're ready, I will ask you some questions that showed up while you were speaking. The first one is asked by Magnus Becker, and he's asking why aren't you then not mentioning sodium batteries in your presentation or in your project?
Yes, certainly. In this particular case, it was a limitation of the call itself. Sodium batteries were considered to be outside of scope for the call.
Okay, thank you. So the second one is from Belika Waragoda, and he's asking what type of new thermal management techniques are you looking into through this project? Sorry.
So in Tempest, we're looking at thermal management from two different ways. First of all, we're using methods to improve heat dissipation. And then second, we're implementing two different methods for lightweight heating of cells, either in cold environments or in cases where the cells need to be maintained at a higher temperature for better operating characteristics.
Perfect. If at any time the participants that asked the question consider that their question was not answered or was partially answered, you can type it in on the chat. I don't think this is the case, Jeremy, but this only came to my mind. And the last question for the Tempest project is from Gaston Strong. And I think it's relating to the Magnus Becker. So to the first question, he asked if why you didn't mention LIS batteries.
Well, it's basically the same thing. Lithium sulfur batteries were not within the scope of the call.
Okay, perfect. So let's go with the fastest project. We do have only one question for you, Alvaro, but then there are two for extended project. So Luke Perrin is asking, how does the cell-to-pack designs align with sustainability target of easy recycling of the battery? He says, specifically, there are known issues with current cell-to-pack designs around dismantling and discharging, repairing with cell level issue.
I'm not sure if this question is for me, at least for fastest.
It was asked during your presentation, so maybe it's for another project. I don't know. This was for Tempest project. This saying, look. So Jeremy, if you can answer, maybe I
Certainly.
can.
Yeah, for our particular case, we are designing the packs from the ground up to take this into account. AP Plus Rescol has developed a type of reversible joining system that we will use for the complete assembly of the system, so that at end of life it's very easy to cleanly disassemble not only the composite housing, but isolate each of the cells and then treat the cells for end of life processing.
Thank you. So we can jump into the questions for extended project. Alvaro, Seidu Heavy is asking, the solid state battery are already mature, manufactured. What is the chemistry behind it?
So the chemistry is cathode LFP, anode lithium metal, and electrolyte oxide polymer. If it is mature enough, we are working on that. It is not the focus of the project. As AVI company, we are cell provider for the project. It is mature enough. It is something that we have to discuss inside the project with the safety requirements and thermal characterization.
Thank you. And there is also a question from Luke Perrin. He's asking, how is the BMS wireless system ensuring a reliable system that is sure not to fail in the middle of operation?
We can use different ways or both together. The first one is redundancy. For extended, we are using one sensor per cells. So if in the module or in the pack we have 16 cells, we have 16 different sensors. So it means if one fail, probably we will be using the cell, the sensor that's in the next cell. It's not act as if something happened. I mean, the temperature from one to another doesn't change so much. So it is one point. With several sensors, we create some redundancy and then robust communication protocols as much as we can. And then as well, fail-safe mechanism, let's say. This mechanism is activated in case of detect a fault or a system anomaly in the system.
Perfect. Thank you, Álvaro. So we will go to the questions that were made to VERSAPRINT. Lisa Lu. The first question is from Seydou Ebi, and he's or she is asking, do you expect any big change in the BMS because of moving from conventional Li-ion to solid-state system?
I'm not sure this question is for us. We don't work with solid-state batteries.
Okay. Okay, maybe this was for another project, Seydou. I don't know if you're still in the webinar or not. Okay, we can go for the next one. Sorry. I need to make clear that I'm not a technical expert on the topic, so this is quite hard for me. Luke Perrin is asking, are the material used polymers tested for thermal, mechanical, or chemical recycling process?
Yes.
He's asking, are they reacting well to combination, separation, and recovery techniques?
So yes, so we are trying, we have a whole task dedicated to this, so to chemically recycle them. So we are going to use this SRP, we add the additives, and then we are going to use different techniques. And the goal is to find the best one. So among them, we are going to use supercritical CO2 extraction, selective dissolution precipitation, and others. Yes, what we expect and what we are choosing the polymers and the flame retardant and the phase changing material in order for them to be separable and reusable.
Thank you very much, Lisa Lu. So next questions are, well, there's only one question for BATs. Magnus Becker is asking, what is CAM slash AAM, sorry, chemistry?
Yeah, actually, I saw the question, but I did not get what. I mean, I don't think I said nothing about CAM/AAM. I said that we are using Gen 3B technology, and it is requested in the. It was requested in the topic to use advanced technology. I think, and Gen 3B it is basically NMC with silicon graphite in the anode.
Okay, so we, well, if Magnus Becker is still in the room, you can clarify this, on the chat. Meanwhile, Seydou Ebi clarified that the question before, the one that I thought was for VERSAPRINT, was for TEMPEST. So, Jeremy, if you want, I can repeat it. He asked, do you expect any big change in the BMS because of moving from conventional Li-ion to solid-state system?
Well, we're addressing both types of batteries in the project. So our battery management systems will be adapted for each type. Insofar as do I expect any major changes from that? Well, as I said, they'll be custom designed for each of the different types of configurations. I think the most important change that we'll have to bring into the battery management system is more in terms of the structural health monitoring system, in order to make that intelligently interact with the BMS system.
Perfect, thank you. Well, just for clarification, Yosu, the person who asked the question said that his or her question was answered. So thank you very much. And then we can go for the NEXTCELL, the questions addressed to NEXTCELL. So Sarah, I think you also have the support from Li Yuan, who is the technical coordinator of NEXTCELL. So there are two questions. The first one is how the gel electrolyte will be applied in the cell and ensure their existence in electrode layers.
Yeah, we can see
Yes.
Leon. Yeah, go on.
Yeah,
Please.
so I can answer the question. So how gel electrolyte will be applied in the cell is actually by extrusion dry process. So this extrusion dry process is developed by our partner, CEA and Sansico. So they have this technology to ensure there is no electrolyte leaking from the electrons. And okay. I saw another question for recycling, so maybe I can also answer that question as well.
Yes, I will ask it to you, and then you can answer. So Luke Payton is asking, are the various known recycling methods considered for the recyclability of jelly-side cells, or is a new recycling method considered?
Yeah. So actually, we will start with the non-recycling method is hydrometallurgic. However, the disassemble process will be more complicated because we have electrolyte trapped inside the electron. So additional process will be needed for additional process will be needed for dissolution of this geopolymer electrolyte, and but overall this recycling method is none. Yeah.
Thank you very much, Leon.
Thank you.
We will change to NEXTBAT, Miko. There is one question for your project, and Adnan Tazdemir is asking, what is the size of a semi-solid pouch cell? Any update for energy density or capacity?
We are actually in the sourcing phase of the cells. We have a few candidates, but what we can say that the options are large format pouch cells, roughly between 50 and 100 ampere hours. And was it also, what was the second part of the parameters that?
You want me to read the second part of the question?
Just to complete, the final choice has not been made, so we're not ready to tell the final details of that, but semi-solid state, so mostly solid electrolyte, but some liquid electrolytes in there, kind of in between the solid state and let's say N3B.
Okay.
Area.
Thank you very much. So these were all the questions asked for the specific projects, but we also have a last question addressed to all the projects, which was made also by Adnan Tazdemir. And he said that he thought, or he or she, I think he, thinks that all participants should explain their target or abilities for project in terms of scalability or sustainability. I don't know if this is a quite long question to answer, but in case of any one of you wants to answer, just you can jump in, maybe raise your hand before.
I think one thing that needs to be pointed out, at least for the 5 projects that were funded under the aegis of the call under which Tempest and the 4 of the other projects, VERSAPRINT, BATS, Extended, and NEXTBAT, is that the call itself is fairly limiting in the final technology readiness level. And so the goal is not to go to full scalability. For example, direct integration in an application was essentially forbidden by the call. And so the ultimate goal here is to develop technology, at least, from my point of view speaking, at least with respect to Tempest. The goal here is to develop key technologies that can be applied as a platform, and then eventually scaled later on. But in order to achieve that, we work with partners who either are involved or who have connections to gigafactories to eventually explore scalability routes in the future. But I should be clear that the final technology readiness level of many of these projects, at least under the EU Ingenious cluster, is not to achieve, for example, TRL7 or TRL8. That's outside the scope of the project.
Thank you very much, Jeremy. I don't know if any of the rest of the participants want to add anything to this question. I don't think so. Oh, Alvaro? No. I thought you
I
were
don't
going
think we
to
have more
Dharma.
questions. I wanted
No?
to say that we will make a follow-up email, so all the speakers and all the project coordinators and managers, we will send their contacts and their social media and their website. And this video will be available on YouTube for, next week. And we're just right on time. The webinar was supposed to finish in 3 minutes, so I think I will close up. And first of all, I would love to thank every speaker and my colleague Danny for all your help. We have been organizing this webinar for, I think, 2 months already. So I think it was great. Thank you for the information. And I hope it was very interesting for all the participants. And yes, you will receive this follow-up email as we finished. And thank you for your time.
Thank you, everyone, for your effort
Thank you.
and motivation. So, yeah, it was a great webinar.
Yeah. And as Lisa Lu was saying, I think we will see each other at the BIT in Barcelona in November. So most of the projects will be there. So we'll see each other face to face.